Hello guys, today we're going to be going over some very common problems in linear algebra. So we're going to do this pretty fast, and I'm going to assume two things. Number one is you know what reduced row echelon form is, and two, you know how your row operations work. If not, then I'll just point them out when we do them, and you will be pretty familiar. Anyways, first question is asking us to write down one way to convert A to B using elementary row operations. Again, elementary row operations are really just when you do something to a row, for instance, R2 minus 2 times R3, or if you do like 1/2 times one row, or even if you were to do something like row 3 switched with row 2, all which are very valid and very fair because they all maintain the matrices functionality, right? Stays the same, this relation is the same. So in this sense, we're going to convert it from A into B. And so how we're going to go about this is none other than the following. So what I would think about is, well, we see that this row and this row are the same. So we're probably going to want to do something along the lines of keeping that there. But this and this are also the same. So the first thing we're going to do is switch row 2 with row 3. And that's going to give us 4, 5, 6, 7, 8, 9, 1, 2, 3. Then secondly, what we're going to want to do here is we're going to want to essentially subtract in a way that we can get this here, right? So we know that we switch this rows here, but this row is not the same as this one, right? This row is not the same as this one, which is the one that we switched up here. We move this up here, but it's not the same. So how do we get that there? Well, you notice that the difference here is essentially 1. And what is the difference between 2 times 4 and 7? That is 1. 2 times 5 and 8, that is 2. And what is 2 times 6 and 9? The difference is also 3. So it essentially works perfectly. So what we're going to do is row 2, right, minus R3 minus 3 times R3. R2 times R3, right? That should work for our R2. It's going to be our new R2. And so we're going to do 1, 2, 3. And then here what we're going to get is a -1, -2, -3, as we already did our logic-based argument there. And that's beautiful because now we can just do, we noticed that the last thing to do to match our wanted, our goal matrix is literally multiplying by that negative in R2. So it's going to be -1 times our R2. That's going to be our R2. And we're done. I mean, that's all we need. 2, 3. That'll be 1, 2, 3, 4, 5, 6. Done. And you see that matches exactly what we have up here. And now the next question is, can you use elementary row operations to convert B into A? What are those compared to the one before? And you notice that the ones that we're going to have to use are literally the opposite. That's interesting, right? Because that's how matrices work. So we want to go backwards. What we're going to want to do is, again, multiply the R3 by a negative in this case, right? And so why does this work? Well, in this scenario, what I would do is if you multiply the R3 by the negative, and then, so like for instance, if we did this, R3 times the negative, right? Well, this turns everything into negative here. To convert B into A. And so then what you want to do next is you're going to do R3 is going to be R3 minus 2 times R2, right? Essentially the opposite. And then finally you're going to do R2, 3 converts with R2, and we're going to get exactly that. So you're just doing the operations backwards. Easier way to see it is like if you have like 1, 0, 0, 1, and you go forward, you do R2 plus 2 times R1, right? You would get 2, 1. Let's say this is our R2, 2 times R1. If you want to go backwards, all you have to do is R2 minus 2 times R1. It's going to be a new R2. And you literally go backwards. So that's kind of the main idea there. That's important later on in inverse matrices. Don't worry about that. I'll take you guys through the whole issue. Pretty straightforward. But essentially that's got to do with inverses and taking it backwards. Just a little cool thing to notice. Now, what is the fewest number of elementary row operations that we can do to transform A into B? That's where it gets interesting, right? Because the fewest one, if we notice the difference here, is mainly the fact that because R depends on both R1 and R2, we need at least 2 row operations to convert R2 into R1. So we know that first we switched it, right? We noticed that we switched it. That's already one operation. But then when it was negative, we still had to do another operation. And that was after we had already added it. So we did a summation of like 2 minus 2, right? Something like around those lines, just a random operation I'm doing. And then we flipped it. Well, we know that we had to flip it, right? Because that's the fastest way to get there because it was already done for us. And then you had to do this operation, and then you had to multiply by a negative, right? So there's 3 necessary operations, given that R3, the resulting R3, depends on both R1 and R2. So that's something to ponder on. But yeah, you can play around with different numbers, but I'm pretty sure you cannot do less than 3 row operations. Beautiful, beautiful, beautiful. Okay. What about the next question? So the next question is really asking us, find all possible values of C which the system does not have a unique solution. So what does that mean? Well, a unique solution in terms of matrices really looks something as follows. Unique solution is one that has a variable. This is how it breaks the columns, or the variables. You had a variable that gives you a unique solution. So this could be 0, this could be any value, but as long as there's something that tells you, it could even be the trivial, which is just 0, but that tells you that x1 is equal to this x1 is equal to something, right? So we do not want that. And there's 2 possible situations where that doesn't happen. One is where there is no solution, and that essentially means that we got a constant. When no solution, you got 0, 0, 0, and a constant, because that's impossible, right? You cannot have some zeros equal a constant. It's impossible. Or you could also have 0, 0, 0, 0, and assuming that this is a free pivot zone, meaning there's no first, like if it was something like this, see how there's a little ladder here? You see how this column here has a first non-zero number? Well, then that's not an issue. But if you had something like this, where only these 2 columns, x1 and x2, have a first non-zero value, then that implies that the x3 is a free pivot and thus a free variable. And that means that you have infinitely many solutions. But if you only had this one here, then that would imply that you do not have infinitely many solutions. So let's just go on about solving this. And I think the main idea how you do this is pretty straightforward. All you have to do is essentially play around with how we move this around to get to the situation where we have 0, 0, 0, 0 or 0, 0, 0 with a constant, because that's not allowed. So that would mean no solution, inconsistent. Or here we have infinitely many. And so how you want to do this is, my trick is to get all the non-unknowns on top. So we're going to switch row 2 with row 1, right? So what we're going to end up with is going to be 1, 2, 1, 1, right? C, 1, 2, 2, 1, C, 1, 1, 1. And then the next thing I want to do is, I notice I want to get this what we call row reduced echelon form, which is what I assumed you guys knew a little bit about in the beginning, which is just 0, 0, 0, 0, 0, 0, 0 with some constants here. And the idea is that you have the zeros along the diagonal, and that's going to make it very simple to solve for your x1, x2, and x3, right? Because all they are is the answer is here, right? So this x2 is equal to z, this x1 is equal to c, this x2 is equal to c, and this x3 is equal to z. And so what we're going to do is essentially just keep solving until we find it. And so what I'm going to do here is R2 minus C times R1, right? Beautiful. And so what we're going to get is essentially going to be 0 here, and it's going to be R2 minus 2 times C, so it'll be 1 minus 2C, and then here will be 2 minus C, and then here will be 1 minus C, right? That's pretty straightforward. Just treat your C's like any other value. Beautiful. And then you notice that we can also do, by the way, this is our R2, and then we can do the same for our R3. But in this scenario, we don't have to deal with the C's, so we can just do R3 minus 2 times R1, and then you got 0 here because it's 2 times 2 minus 1, minus 2 times 1 is, yep, negative 3 here, and then we got C minus 2. and this is the same as 1 minus negative 2, or 1 minus 2, which is negative 1. So we got to this situation here, and you notice, well, we still not quite there, right? We don't really have this 0, 0, 0s, and we like to be able to solve for the top variables in this column-like manner. Yes, you're right. So what we're going to do is essentially think, well, how can we do that? And the only way to do that is to get rid of this. How do we get rid of this? Well, we can multiply the row 2 by the following. R2 times 1 over 1 minus 2c. That's going to be our new R2, because that would mean that this whole thing here is going to be 0, 1, 2 minus c over 1 minus 2c, and then 1 minus c over 1 minus 2c. And you can see that it starts delving into a little bit of algebra here, because you're going to have 1 here, you're going to have your, you have your thing at 3, you have your c2, and you're going to have your negative 1. And a little bit of algebra arrives here is that essentially you're going to start being left with some quadratics when we remove this here, right? So what we're going to do is r3 plus 3 times r2. What does that give us? For that was our new r3. Well, the answer is none other than, and then let's make this beautiful up here. Oh, sorry, that was not what I was looking for. 1, 2, 1, 1, 0, 1. And this is going to be 2 minus c over 1 minus 2c. And this is going to be 1 minus c over 1 minus 2c. And this here is going to be 0. It's going to be 0. It's going to be 2c. It's going to be, we're going to actually solve for those right now. The idea is that you should be left with the following. Let's just get some room for me to solve this here. You're going to end up with c minus 2. And that's going to be c minus 2 plus 3 times this up here, right? So that would just be 6 minus 3c over 1 minus 2c. And that should just factor out to none other than, that should just factor out if you multiply this here, 1 minus 2c, 1 minus 2c, when you multiply it out, right? I just did this. Just you should be left with c minus 2 and then minus 2c squared plus 4c plus 6 minus 3c, and that all just cancels out to, it'll be c, this will be 2c minus 2c squared, and this will just be plus 4 over 1 minus 2c. And if you simplify this by factoring out the negative 2, you should just be left with c squared plus c plus 2, which essentially just yields none other than the idea that it's c plus 2, c minus 2, and this is c minus 1, right? And so that's important. I'll tell you guys right now why. Because you notice that if there's a 2 here, that's going to yield 0 in this term, which gives the whole thing 0 here, right? But what about here, after we did this, after the addition? Well, to make that 0, it's going to be 1 minus c, right, times 3, 3. And then here we're going to have 1 minus 2c, and we're going to be adding it to the negative 1. Well, that's the same as essentially saying, negative 1 c squared plus 3 minus 3c all over 1 minus 2c. And that's essentially going to give you, none other than, you see, that would be just the same as saying negative would just give us negative, that would just give us 2 minus c over 3. So that's the same idea. And so what you notice here at the end is that you have this, and this. And all that we're going to look at is that if we already have 0, as I told you before, this implies that when this is a 2, when c equals 2, we're going to have 0 and 0, and that we have infinite solutions. But if we have z is equal to, say, 1, or 1/2, negative 1, that would make this 0, right? So we would have a 0 here, and thus by having a 0 here but not on the other side, that would imply that we have essentially an inconsistent system. So those are the two possible ways, if c equals negative 1 or if c equals 2, in which we can have a non-unique solution. So yeah, we use some algebra too.